So in this module 2, we have covered up till threads. So till this part we have covered up already. What is being required for your internals, it has been covered. Okay. And the questions I'll give you. The questions are very simple, straightforward questions. Explain the concept of process control block in detail. Briefly describe the fundamental state transitions. What do you mean by threads? Explain the threads concept in detail. Right? So there are 4 questions here. Okay. So this 4 questions we can prepare, and let us see this part also, and let us decide on Monday whether till we use. Now only if you can tell me, I'll fix the syllabus contents for you. If you are fixed with it, can someone comment on it? So this is what we are dealing today. Kernel and user level threads is what we are discussing now. Okay. After that, we have left out with 3 more concepts. If these 3 concepts you have discussed, that will be end of your module 2. It's very, very easy module to understand and to prepare also. It's very easy. Okay. Let us see now threads. From threads we will just discuss. Threads we have already seen. As we have seen, what is meant by a thread? So what is thread actually? What is this thread? What are the applications threads used to? What are the options? Applications which we use the concurrent process. Why is this used to speed up? So we have the speed up of the process. We can able to do this. So this concurrent process, what we are trying to do, is useful for us in speeding up the process. Correct? So we are trying to use the applications where we use this concurrent process. Fine. To speed up what? To speed up what? To speed up their operation. That's how the slides will be. So this threads will be useful. Correct? Yeah. Now, what is that here in switching? You can see this here. The switching is going to happen. Switching is going to happen. Switching between what? Switching between the process. Between the process. Between the process. It's like between. Right? So between means what? So between means what? 1 to 1. So it's like when we try to move it from 1 to 1. Okay. So it's like moving from 1 to 1. So from here to here. Switching will happen from one process to other process. Let us say, for example, we have one process here. We have one process, right? We have one process here. So let us say we have one process here. So this one process, what will do one process? What will do? We have something here done with one process. So let us say this is one process, and we have some other process here. Let us say this is second process. Okay. To switch from 1 to 1. From again we have to turn back from second to first process. It will take a lot of time now. So let us say this is a process here, P can write, and this is also process we can write P. Where this inside this process we have something called threads. Let's say this is like a thread here. Okay, something like this we have a thread. Now switching from one thread to another thread, it is easy. Compared to switching from one process to other process, switching from one thread to other thread will be easier. So that's what the application of this threads comes into picture, where it makes sure that the process is very simple for us to use, and it is not having any overhead to use here. There is no overhead here to be used. So that's very simple and that's easy, right? And let's look at the third point here. What is the third point here? A thread is an alternative model of program execution which provides concurrency with less overhead. So it's an alternative model of program execution which provides concurrency with less overhead. So we know that overhead will be cost whenever you are using a big process. So that overhead can be minimized by using this threads. Okay. Yeah. So that's what we have seen, and we have seen the switching of the process will have two things, two overheads. One is execution related overhead will have. The other one is what? One is based on execution, we have the overhead. The other one is based on resource overhead. So execution overhead means what? Whenever you are trying to move the data from one place to other place, or you are executing a program, okay. So what will happen is you need to carry the CPU state also. The CPU state what we have here, this has to be carried. The CPU state what we have here, right? So this has to be carried. The CPU state of the running process has to be saved. You have to save this, and the CPU state of the new process has to be loaded. So because of this problem, we need to do two things here. We have to save this, right? And then we have to load it. We have to save this and we have to load it. Where you have to do that? In the CPU. So this is overhead which is unavoidable. This overhead cannot be avoided. This overhead is unavoidable. So this is what happens in your execution related overhead. Is that clear to you? So it's very simple for you. Let us say we have a farmer with us. Okay. If the farmer has to sell his goods, okay, he has cultivated, let us say this is season for mangoes. So mangoes, he got a lot of mangoes are there in his what's the planting area. Now he need to sell that to the market. What will happen for him? Along with the cost of production of the mangoes, he need to transport that to the market. Correct? That becomes an overhead for him. That is an extra burden for him to transport it because nobody else will bear the cost of transportation. That is called overhead. Okay, and you take for example from your side, uh, you have you have joined any institute or you have joined the school, correct? School fees you'll be paying, but along with the school fees, you have to bear your transportation fees. You have to bear your expenses for your breakfast, lunch, and all that when you are traveling or when you are staying there somewhere like that. That's called overhead, which means along with the thing what you had, some more additional things will come. That's called overhead. Okay. So here the overhead is what? The CPU running state has to be loaded along with the process. Along with the process when switching, we need to make sure that this also has to get switched. This also has to get switched, which means we need to save the content and transport that also and load it in somewhere else. That becomes overhead. The next is the resource use related overhead. Whenever you are trying to use the resources, we need to get the overhead. What is this? The process context also have to be switched. So we need to switch this process context also. We need to switch it. Okay, what it involves? It involves switching of the information about resource allocated to the process. So we need to switch the information. So let us say process one requires access to the Bluetooth device. So whenever you are switching that, the Bluetooth device access has to be disconnected from process one. If you are trying to switch from process one to process one uses Bluetooth, process two uses Wi-Fi. The Wi-Fi resources has to be cut down, and Bluetooth resource has to be given, or vice versa. Okay. So resource allocated to the process, such as we need to switch what? Memory and files. So what is that involved here? This memory and files are involved and the interaction of the process with other process. So we need to interact with the other process. For example, the process P1 is switching to process P2. Now process P1 uses Bluetooth. Process P2 also uses Bluetooth. Then what to do? Whether we need to switch that also or whether we need to leave it and start afresh, all that has to be taken care. Okay. The large size of information adds to the process, adds to switching overhead. So as we are switching the process, along with the process, this information also has to be carried. That becomes the overhead. So large size of information. Okay, this is going to add the overhead. Is that clear now? What is that happening with this? Yes. So next, threads. Okay, the process creates a thread. Who is going to create the thread? The process is the one who is going to create the thread. How it will create? Through a system call. Through a system call, we get the thread gets created. Fine. Now, so thread operates within the process context. So this thread is going to operate within the process. Thread is going to operate within the process context, not outside the process context. Okay. Next, use of the threads effectively splits the process into two parts. How many parts it will split here? Into two parts. Split into two parts. The one is resource state. The next one is CPU state. The two parts it will split, we told, right? What are the two parts it's going to split? Resource state and then CPU state. So the spread operation will be executed and it will split the process into two parts, resource state and CPU state. Okay. So whereas we switch in between these threads, whenever you are trying to switch between the threads, right, which will incur less overhead compared to the switching in process. Switching in threads will be incurring the less overhead. So less overhead means what? No need to carry too much of data from the resource and too much of data from the CPU when compared with the process. Okay, when you switch from one process to other process, compare that with switching from one thread to other thread, we will get less overhead. So less things has to be carried out. Okay, so that's what we have seen, right? During your IPL, what happened? Both the teams will not move, right? During the IPL season, what happened? Both the teams will not change their locations. Correct. The four teams will be there only. They will play. After that, two teams will change from there. Two other teams will come here. So which has reduced the overhead. So before both the teams has to move sometimes. That becomes a lot of overhead for them to travel all the goods what they have with them, right? So like that it is. So which means you do like this, what will happen? The overhead can be minimized. Overhead is minimized means the processing speed can be increased. So much more effectively it will function. So that's what we have seen. So this thread is what? It's an alternative model for program execution. We have seen that. Yeah, we have seen this process and this was the same slide, right? Okay. Now let us look at this one. This is your operation of the threads. So we have a process here. Inside this process, we have the threads. The process can be n number of processes. So let us say, for example, one process we have taken PI. Inside this process context, we have information about memory, about resources, about files, code, data, stack, all the information we'll be having. Along with that, we have two blocks. Process control block we have and thread control block we have, TCB and TCP. This TCB block will have thread control blocks. It's not only one block, then number of blocks. Here there are three threads here. So three thread blocks are available. So along with that, supporting three stack blocks are available, which means like one stack only we have, but the stack block for this corresponding thread one and this thread control block and stack block for thread 2, and for thread 3. So like this we have. Let us see this, what is happening here and what is going. Now, we have seen already the advantages over the threads. What is this means? When I use the threads, we can have a lower overhead. So that's what we have seen, right? So the overhead is minimized. It is minimized overhead because we no need to carry everything from the process. We can carry only that confined to the thread, so that the overhead can be minimized in switching, and we can able to communicate effectively. How we can able to communicate effectively? Threads of a process can communicate with one another through shared data, as they have shared data among themselves, so we can able to communicate effectively. So that because of that reason, we can able to avoid the overhead of the system calls for communication. Okay, as we have common resources, we can able to communicate effectively. Right. The next, simplification of design. How the design is getting simplified. Okay, so the code length is minimized, right? And the applications, we can use wide applications, so that becomes much more easier and simplified. Use of threads can simplify design and coding of applications that service request concurrently. So we can able to do this process in a concurrent manner. So we can able to simplify the design when we use threads over the process. Okay. Now, how do these threads are classified? These threads are classified, one based on kernel level, first one. Second one is user level, and third is hybrid. What is what? Kernel level, user level, and hybrid level. So what is the meaning of this? Similar to like this. So whenever you are trying to log into your Windows operating system, okay, you may have something like this. You may have admin portal, user portal, and some other guest portal. Correct. So admin portal is similar to like your kernel, and user portal, like we have seen user portal. We know that user portal we have like admin, like student portal, admin portal, and guest portal, something like that we can see, right? So this is like kernel, user, hybrid. Hybrid means the combination of user and kernel both. Some things will give the access to the kernel, some things will not do. That's a hybrid thread. Now, see this first one, kernel level threads. First one is what? Kernel level threads. So threads are managed by the kernel, which means the kernel itself is going to manage the threads. Whereas in threads are managed by the thread library. So we have something called thread library. So this thread library will manage the threads. Then whereas in case of hybrid threads, the combination of kernel level and user level threads. Combination, which means some features of user will have, some features of kernel will have. Okay, the hybrid thread. So let us see now kernel level and user level one by one. So first one, kernel level threads. Okay, so a kernel level thread is like a process, except that it has similar amount of shared information. So it is same like your process, except one thing it does have, it has small amount of information. It does not have too much information. It's smaller amount of information. Smaller amount of information it is having, which means it can able to reduce the overhead. It is same like process how it executes, but you have a smaller information. Next, switching between threads of same process incurs the overhead of event handling. So how we are able to manage that switching over? We can able to manage that by using event handling. This mechanism we are trying to use to manage the switching over the threads. Let us see now here. We have one process. Okay, so this process have 3 threads. Okay, and 3 of the threads are controlled or reporting to the process control block. And you see second process. Second process here, it is, let us say, is pi and pj. Okay, some random variable name we have given I and j. It can be p1, it can be p2, provided I value is 1, j value is 2. Now in this we have only two threads to execute. So thread 1 and thread 2. These also are reporting to the process control block PCB. Okay. What are these blocks? So these blocks are thread control blocks. So which means we can see the connection between threads to thread control blocks and thread control blocks to process control blocks, because the construction of all the threads is a process. So what we are trying to do, we are trying to control the thread. Once the thread is controlled, all the things are ready. We are sending information to the process through process control block. Similarly, second thread information will pass on to process control block. Third thread information pass on to process control block. Now, when we are trying to communicate from process 1 to process 2, or thread control block to PCB, or thread to thread control block, so all these things will be scheduled. The help of a scheduler. Okay. So scheduler, what it will do? So when you see this brown color one, so the brown colored one is selected PCB. So we can call that as selected PCB, and which is pointing towards that is called as PCB pointer. This arrow mark, what is pointed, is called as PCB pointer. So let us see something in detail about kernel level threads. Further, let us try to understand now user level threads. Okay, same. It is looking like same user level threads also. But what's the difference here? This process context, see this difference here. The process context is managed by event handling. Like with the help of event handling mechanism, these are going to come. Whereas here in this case, so as the kernel is not involved here, fast thread switching is happening. As the kernel is not involved, we are able to do the switching very fast. For example, like if you have something, any queries you have, what you'll do, you are asking directly to me, or you have any queries, I told to ask, put it in WhatsApp, I'll check it and tell you directly. So that way we can able to access directly. Or I'll tell you, okay, whatever doubts you have to ask in group only. Then what will happen, one by one, you'll start asking. Let us say I'll raise my hand here and I'll ask you, sir, I have some doubt. Somebody also will raise their hand and ask some doubt. So in that case, what will happen? The kernel is like someone who is deciding that, okay, you get the access, you don't get the access. But whereas in case of this user interface, they are able to get the access directly. The switching is happening faster. Okay, from one thread to other thread, we have the very fast access. Okay, and blocking of a thread block, all threads, blocking of a thread block all the threads of the process, no concurrency or no parallelism. So whether we do not have any kind of concurrency, no concurrency or parallelism. We are not able to do anything concurrently, and we are not doing anything parallelly, which means one thread is running, other thread has to run, like that we are not doing it. So one by one we are trying to do and complete it faster. Okay, this is how we have. So same mechanism. You can see this here, thread control blocks we have, and we have something. This is what these blocks are. What process control block. We are trying to map. Okay, this we are trying to map the corresponding thread control block to the process control block based on the thread library. So whereas here we are trying to do with the help of event. We have a scheduler we have, and we are trying to do with the help of that. And this also is looking same. The scheduler also we have here, but what we did here, the difference is we are trying to map it here with the help of user thread. This is called mapping we have done. But whereas in case there is no mapping, whomsoever want to access can access. If you don't want, you don't need to access. We'll see that in detail. Okay. I'm just trying to give you an idea what is the difference of user level thread and kernel level. So now scheduling of user level threads. So what is this ABCD actions of thread library? So NRB indicate running state, ready state, and block state. Okay, running state, ready state, and block state. So N is not ready, right? Or let us say N is running, R is ready, and B is blocked. So this thread will state that, this thread block will say that which is running, which is blocked, or which is ready. Okay. We have something H1, H2, H3 are the states of this thread. In same way, we have taken 3 threads for all the process, P1 process, we have all the process we have here. Now you check here, this is only PI process, which means only one process. You see the difference here. Whenever this thread is connected to H1 is given for this. H1 is what? It's block state. Okay. So whereas in case of process control block, we have ready here. And N is given running state. N is given running state. And again here N is given block state. So let us see what is happening here with the help of thread libraries. Okay. Thread library maintains thread state and performs switching. So this thread library is what is going to maintain the or perform the switching of this. Okay. Thread hybrid thread models. Hybrid thread models you see here mapping also we have done, and we have done the alignment of PCB also. So both, like this is there in kernel. This was connected through user. So both the features of user and both the features of kernel are used. First one is what? Many to one. So many are there. We are connected to one of the PCB. Second one is one to one. One to one is what? See here, many of them are connected to single user. It becomes many to one. Whereas here one to one thread to one process, one thread to one process, we have connected one to one. And third one, many to many. So this process can access any of these KTBs. This one can access any of them. So many to one. So like this, we are able to connect and use them in a hybrid manner. Let us see one by one what is happening with the user kernel level threads. Okay. Please note down the working of this the kernel level threads. So first what will happen is the process will make and create a thread. How the process will create a thread? By using system call. So first point. You can keep the heading working of kernel level threads. Working of kernel level threads, and the working of this as per this block diagram I'm talking about. Right? You can please make a note of that. Let us see one by one. Working first point. The process makes a create thread by using system call. The process is going to do that by using system call. After that system call is assigned, system call will create a thread. What the kernel will do? The kernel will assign the ID for it. The kernel will assign, and second point is what? The kernel assigns ID to it. What ID? An unique ID it is used for which one? For a thread. And it allocates a thread control block. So corresponding to the ID, it will allocate a thread control block. You can see that here. Let us say this is a thread. Okay, the thread is created. It will have its ID, and correspondingly, it will give you the thread control block. So this one is thread first. After that, second thread is created by kernel. Second thread will be given thread control block. Third thread is created. Third thread is given a thread control block. So that's what will happen in the initial case. First and second point. Third point. What this thread control blocks contains? This thread control block, we call it as TCB shortly. It will contain a pointer. This TCB contains a pointer. So what this pointer will do? It will point to the PCB of the process. It will point to the PCB of the process. This thread control block will have a pointer. It will point towards the PCB of the process. Same, it will have a pointer. It will process to the PCB of the process. Same third one will have the pointer, which will point towards the PCB of the process. So this is what is happening initially. Further, what will happen? When any event occurs, the kernel saves the CPU state of the interrupted thread in its TCB. Whenever suppose any interrupt occurs, let us say everything is done and saved. Now we have some interrupt. Let us say someone has pressed the switch button. Let us say you take coffee machine, you take, or someone is using something with mouse cursor. Something is happening, some event is happening, and what it will have, what it will do? The kernel will save the CPU state of the interrupted thread in the TCB. If any event occurs, this TCB will save the current state of the thread. Okay, when an event occurs, if there is no event occur, nothing. The CPU state will be running freely. It will not save any of that. If any event occurs, then the kernel save the CPU state of the interrupted thread in the TCP. Whenever it got an interrupt here, for example, thread 1 got an interrupt, that corresponding thread 1 interrupt state will be stored in the TCP. So that's what. Okay, next. That is during when event occurs. When the event is happened or event is handling, let us say, after the event is handling, the scheduler considers all the TCPs of the threads and select over ready thread. So once we complete that, when we are handling it, we should be able to make sure that yes, this thread is ready or it is blocked or it is in running state. So the scheduler will decide whether what is the state of that based on the CPU, whether it is running, whether it is ready, or whether it is blocked. That is going to decide by the scheduler. Okay. Now, the dispatcher uses the PCB pointer in TCP to check the selected thread belong to different process than the interrupt. Let us say a possibility is there now, right? Sometimes we can get a event from this process and sometimes we get an event from other process also. So this scheduler will select whether, find out whether these TCPs are acting for the corresponding process or something else is going to verify and check it. After that, it will save the content of the process to which interrupt thread belongs to. So what it means, it all the data went to PCBs, right? Process control block. Now PCB is going to verify whether this came from same process or not. Okay, it came from same process. Then it is going to save the content or the context what it is received. Okay, and load the context of the process to which selected thread it belongs to. So it will load accordingly and state that this process is now it has to report whether this corresponding process is being completed or running or what. So based on the input from TCPs, the PCB will act. Okay. Now, what is the advantage of using this kind of kernel threads? Advantage is what it has similar amount of state information. So what PCBs will have, TCBs also all consolidate will have same information. The information is not extra or not less. Information we are able to maintain it, first thing. And we can able to achieve parallelism. In multi-processor system, we can able to maintain something called parallelism. And we can able to improve the speed of the processing. Other advantages. What's the drawback of this? We are switching between the threads, correct? As we are switching between the threads, and it is being done by the kernel. Okay, so there is some overhead for the kernel. Before kernel is free. Now we are switching from one thread to other thread. So this kernel is going to do it because we are trying to do this using kernel based, correct? So what is this kind? This kind is what kernel level. As we are doing in kernel level only, and when you are switching from one thread to other thread, the kernel will have some overhead. So that is the disadvantage. So because of this, what will happen? Because of the overhead, okay, the selected thread belong to the same process or not, we can able to identify. So this is one of the drawback of the overhead. Let us move on to the next one. Any doubts so far? Any clarifications?
No, sir.
Is that clear?
Yes, sir.
Please try to note down some key points, 1 or 2 points, so that from there on you can construct the story. It's very, very simple and easy module, but the words are new for us, so it may take some time. But once you read, right, it's very easy. Just understand the block diagram and how to explain it, what all things are there. It's very good and easy. Yeah. The next one, how it is working, let us see. Which one? Next one means user level threads. What is happening here? Let us see. And to cut short in the kernel level threads, what is that to cut short here is the advantages what we have, the speed is getting increased and we require all the information we'll have. Advantage, drawback is what we are going to get some overhead in the kernel. As to minimize the overhead from the kernel, we are moving on to the user level threads. Okay, overhead we have in kernel. Let us try now user level threads. What is happened here? Let us see. Okay, user level threads. These user level threads are usually implemented by thread library, whereas kernel level threads are implemented by kernel. User level threads are implemented by thread library. Okay, and with this thread library is what it is linked to the code of the process. Thread library will be internally linked with the code of the process. I'll repeat again. User level threads are implemented by thread library, okay, and which is linked to the code of the process. And the kernel is not at all aware of the presence of user level threads. The kernel does not know anything here. The kernel is not at all aware of presence of user level threads in the process. The kernel sees only process. Okay, it does not involve threads. Kernel sees only process. It is very simple. Before what happened is, like let us say you are attending online classes now. Okay, you know how to operate mobile phone, how to log in, how to see. So, and suppose you are at the age of 10 years or below 10 years of age. Some of them may not know how to use mobile phones, but now nowadays the kids are different. They can able to operate anything, right? If you just give them, they know how to do. Let us, but still the parent will monitor them and try to give the access for them, right? When you have a children between less than 10 years of age, above 10 years of age, so their parent is controlling the access. Parent is going to view and access and log in them and keep in front of them. Yeah, you can see now, and they'll go and do their work. But that is not that in case of you. There is no kernel involved. Kernel is like parent. There is no parent involved. You are only taking the access, and you are only coming out of that. So that's what user level threads also will do. There is no absolutely no involvement of the kernel, and it is going to use the thread library. So thread library is like a timetable file, which is linked to the timetable. So like that it is. Okay, to make it simple to you. Now, what is the creation of an operation of this? What is happening here? How it is getting created and how it is getting operated. Okay, as we have seen that we have thread library. Okay, the process will invoke the library function. Who is going to invoke that? The process will invoke the library function. So, like simple, like I am going to send a message to you in your group. So, I am a process. Let us say I am invoking you, and to make sure that today we have a class. So, some of them will have a doubt. Today Saturday, right? We don't have a class. How come suddenly it came? You just started thinking something like that. Something like this. It is the process will invoke the library function and create thread to be executed. Now, the library function will create the TCP. As we are seeing here, see the block diagram here. What will happen? Process contains the what is going to do. The process will invoke the thread library and invoke the thread. Now this thread is started, first thread. Once it's started, it will invoke the thread library, okay, or thread control block. This TCP will start getting initiated. TCP will start getting initiated. So the library function will create a TCP for new thread and start scheduling. Okay. Now, now we started scheduling. Now, in case if the thread library cannot find a ready thread, if the thread library cannot find a ready thread, so there are no threads ready to be executed. Now, what it will do? It will make a block me system call. So the kernel now blocks the process because there is no thread ready to execute. There is no thread at all to execute. Then what it will do? The kernel will give something called block. The corresponding complete process will get blocked because one thread is waiting for some information to be did. So none of them is ready. So it will do something called block. Now, now, now if some other thread comes after some time, okay, what this process will do? The process will unblock. The process will unblock when some event activity occurs or when something is getting activated, all that, and it will resume the execution of the thread from the library function. Okay, and this is being taken care by scheduling. Based on the scheduling, it is going to switch and execute the things which are activated newly. Based on that, it is going to function. So let us see an example. Okay, so in this example, let us see something like this one. Let us see an example now here. This one. Okay, how this scheduling is happening in user level threads. Correct. Let us see the example now. Now in this, the thread library manages three threads. You can see three threads, right? So where we have process PI, this process PI will have three threads inside that. Thread 1, thread 2 and thread 3. So we have three threads here. What is N? N represents the state is running. It is running, N will give. What about R? It indicates ready state. R is for ready, P is for blocked. But whereas N they have given there for running. Because ready also R, running also R. So they have used some different terminology for running N. Okay. Running is N, R is ready, P is blocked. You see the first diagram here. What is happening in the first diagram? A. Let us try to understand what is happening in this A. Okay. A. We have a thread called HI. Thread called HI is in running state and process PI is in ready state. How do we know? Thread H1 is running, process PI is ready. The process PI is ready and thread H1 is what? It's in block state as of now here, but when you connect this N to this, so it is running state. Correct. So we can understand like what we can understand, this thread is running, process is ready because N is connected to this. So this is ready, sorry, running, and this is ready. Whereas in case of P, thread H1 is running, process also is running. Okay, let us see A and B comparison. What is happening here? So what is happening in A? Thread H1 is in running state and process P1 is in ready state. Okay. Now, so this thread H1 will resume its operation when process PI is scheduled next. Whenever it is scheduled next, right, it is going to resume its operation. Okay. Like for example, this H will have its TCBs and it have its PCBs. Thread control blocks it will have. It will also have process control blocks. Okay. Corresponding to the thread control block, the process control block is mapped. Okay. Now, for example, this thread H2 is in ready state now. H2 is in ready state now. So correspondingly, its TCB will have the code. If, for example, thread 3 is waiting for synchronization, thread 3 is waiting for its synchronization. Synchronization from what? From thread H1. From thread H1. So, as waiting for the thread H1, so it is in the block state. As it is waiting, thread H3 is getting in waiting state, so it is getting blocked here. See the last one here, it's getting blocked. Okay, it looks confusing here as of now. So what you can do is you just go through it and read from textbook once again, right? And we'll make it simple and try to understand what is happening with the help of H1, H2, H3 and understand what is happening with the user level threads, what it is happening. Okay, and what's the advantage of using it? Let us see this example once again in detail. We have short time to make you understand what is happening. Now let us conclude that with advantages and disadvantages of this. Advantages is what? As the thread is getting involved here, we can able to do it faster. Okay, and there is no overhead from the kernel because kernel is not involved. There is no overhead from the kernel in any sort of communication or synchronization. So overhead is comparatively smaller. So drawback is what? Drawback is what? As kernel is not involved, the kernel does not know what is happening. Okay, so that's one of the drawback here. And as the kernel itself is scheduling the thread library in the process, the kernel also is active. It is involvement also, it is there. Okay, and we cannot able to do anything parallelly. That is one of the drawbacks. First drawback is what? The kernel does not know any information too much about it. Second thing is what? This kernel is involving in scheduling, but what is happening we don't know, but it is scheduling. So kernel is also involved. Second drawback. Third drawback is what? You cannot do anything parallelly in the user level threads. Okay. The next class, let us see how this scheduling is going to work and what is the functionality of this scheduling, and we'll see some example of that with the help of first come first serve based FCFS and shortest request next SRS. So those things we will try to discuss. So let us stop it here, and next class we will see how this scheduling is being done in the user level and how the hybrid threads are work, and some examples we'll see, and we'll start the scheduling part. Okay. As of now, if you look at the syllabus part, so we have discussed about kernel and user level threads. Okay. We'll finalize that in the next class, and we'll move on to the scheduling part. First come first serve base, and FCFS means what? First come first serve base, and next one is what? Shortest request next. Shortest request next. So these two schedulings we see in detail with examples. Okay. So apart from here, now you can decide among yourself and let me know. So this is for 20 marks for module 2. So you want this to be shifted here, or you're okay with that? Nobody is answering. I'll make it till this point, because next IA we'll have only for 10 marks. Module 2, the weightage is only 10 marks. Okay, so you can study till here. You can fetch your 20 marks here, and from this you can easily score your 10 marks. It will be easy. Anything, it doesn't make any difference. Only two questions will get added here: kernel level and user level threads will get added. So it's up to you to take a call. Fine. So I suggest you to take up till here at this point, till what we discussed till now. At this point, you can take it up. Till here is what it is better, because I thought initially 20 marks and 20 marks equal distribution. So now it is 20 and 10 only, right? So you can study up to this point for your internals. Is that clear? Any doubts? Anything?